A sound understanding of the Maxwell equations requires a good understanding of the divergence operation. The divergence operation is related to the divergence theorem, sometimes referred to as Gauss's theorem, which is an entity in mathematics. In its application in physics, it leads to Gauss's law. What does the divergence theory tell us? Divergence theorem. It is about a general truth we're all familiar with. Let's take a lake. And then that lake will have some streams going into it, and it will have some streams going out of it. And we all know that the flux of water through that lake is conserved. The amount of water that goes in there is equal to the amount of water that comes eventually out, unless we have a source underneath or a spring, or we might have evaporation from the lake. If this happens, the amount of water that goes in to the lake is not equal to the amount of water that comes out. And this general truth is pointed out in mathematical terms in the divergence theorem. We might represent the lake as a small cube, like this, through which a vector field penetrates. Maybe like this. Field lines going in and field lines coming out. And the flux associated with this vector field may be visualized as the water going into a lake or into a container of any sort. Now, if we look at this cube, we have 6 sides. There is one, there is another one, we have a top, we have a bottom. If we count all the flux going through all sides, coming out, and all the flux going in, then if there is nothing added, if there is no source inside, and no sink inside. Source means something is added and sink means something is lost. No source, no sink inside, then the flux of water coming out has to be equal to the flux of water coming in. And that's what Gauss's theorem says. Gauss's theorem can be written as the closed surface integral, and that's any surface. That's very important and very helpful in its use in physics. Any complete surface, that's what S represents. In this case it would be all 6 sides, integrating over all 6 sides of the cube, over a vector field, V. So this is now a vector field in general terms, just any type of vector field, not necessarily a water field or an electric field, any vector field. And this is the surface differential, which points upward on each side. So this would be ds. This would be ds for that side. And we have one at the bottom as well, ds. That surface integral, that closed surface integral, is always has to be equal to the volume integral over all the sources inside, all the sources which add or take away from the vector field. dx, dy, dz. This is the divergence theorem. So you can see, for this to work, the term divergence V, the divergence of the vector field, has to identify the sources and sinks, the added flux and the subtracted flux inside the volume V. Note that this V is different, that's the volume of the cube, and V is the vector field. V vector is the vector field. How can this divergence operator possibly identify if something is added or subtracted? It has to look for change, and it does that by doing the following differential operation. So the divergence of a vector field is defined as the partial differentiation with respect to x of the x component of the vector field plus the partial differentiation with respect to y of the y component plus the partial differentiation with respect to z of the z component of the vector field. And this is of course in Cartesian coordinates. In other coordinate systems, spherical or cylindrical, the divergence operator will have a slightly different form. But you can see that what the operation does, if we take an x, y, z Cartesian coordinate system, it looks in x direction. Is there a change? If yes, there will be a positive contribution to divergence of v. It looks in y direction. In the y direction, if there is a change, if yes, there will be a positive contribution to v. And it looks in z direction if there is a change. And if there's a positive change, there will be a positive contribution to the divergence operation. So we get out a scalar that tells us if there is a positive change in either of the three spatial directions. And if that's the case, there has to be a source. If this scalar turns out to be negative, that means in one of those three directions there will be a negative change to the vector field. And that means there is a sink somewhere inside that volume. In words, one might say that integrating flux over a closed surface is equal to the volume integral of the divergence of that flux inside that surface.